Welcome to the Labflow workshop. Today we will investigate the experiment number 12, which is ideal gas laws. The objective of this experiment is to determine the value of the R, the gas constant. You know that gases are described by four properties: the pressure. Let me give you a quick overview of these experiments, and then we will go over the report. So the gases are described by the pressure, the volume, the temperature, and the number of moles. Only three of these four variables are independent. So if we know three of them, we can determine the value of the fourth property. And the equation that relates the four properties is called the ideal gas law, which is this one. Pressure times volume equal the number of moles multiplied by the R, that is the gas constant that has a fixed value of 0.08206 liters per atms per Kelvin and mole, and multiplied by the temperature in Kelvin. And in this experiment, we will measure several properties of the hydrogen gas and calculate then the constant R. We will use this reaction. We will use the reaction of magnesium that reacts with hydrochloric acid to form magnesium chloride and hydrogen gas. That's how we are going to produce the hydrogen gas, measure a few properties, and calculate the R. So let's look at the details of the experiment. Let's look first at the figure 1. We are going to collect the gas in this tube that is closed, this long tube that is closed at one end, and is marked in units of milliliters. This tube is called odometer, and we are going to use this tube to measure the volume of the hydrogen gas produced. And how are we going to perform this experiment? First, we will add 10 ml of 6 molar hydrochloric acid. Look at here at the bottom, hydrochloric acid. And then we will fill it up with water. We will insert, look at this apparatus, magnesium in a copper cage. And then we insert the magnesium ball in the copper cage, the stopper, and then quickly we will invert the entire tube into the beaker filled with water. This is the figure 2. So we prepare first the tube as in figure 1, then we quickly invert it. the entire tube into the beaker that has water. Once you inverted the eudometer, the 6-molar hydrochloric acid that is denser than the water will start to settle at the bottom where the magnesium is located. When we invert, here we have at the bottom the magnesium. When the reaction starts to form hydrogen gas, the hydrogen will displace the water in the eudometer. And some vapor is also produced. And the water level here in the beaker increases as the reaction goes up. And the amount of water vapor depends on the temperature. We will see that shortly. So we measure the temperature of the water bath after the reaction is done, assuming that is the same temperature as the temperature of the gas. We don't insert the thermometer in the eudometer tube. We just measure the temperature of the water bath and assume it's the same. So this is basically the apparatus that we are going to use to calculate the R. So let's look at the report that we have to complete. When you look at the report, everyone will have different data. You are provided with the following data. Look, everything that is in red is given. So the mass of the magnesium, the volume of the hydrogen collected in milliliters, the temperature of the hydrogen, and the atmospheric pressure. And then we will calculate the R using the formula. We know that the R is going to be pressure times volume divided by the number of moles and the temperature in Kelvin. So let's start by looking. Here is the same data. The first thing that they are asking is all this data is given, is the same as the one that is in red. And the first thing that they are asking is the vapor pressure of water. Why do we need the vapor pressure of water? You saw the apparatus that we have. And we need to determine the pressure of the gas, the pressure of the hydrogen. And we will determine it indirectly, in an indirect method. We are collecting hydrogen gas over water. So we assume that the total pressure inside the tube is equal to the atmospheric pressure. So we are saying that the atmospheric pressure that we know equals the total pressure inside the tube. And what is the total pressure? It's going to be the pressure. What do you have inside the tube? The pressure of the hydrogen plus the pressure of the vapor pressure of the water. So they are asking for the vapor pressure of the water because when we need to calculate the pressure of the hydrogen, is going to be the atmospheric pressure minus the vapor pressure of the water. So we need to collect the vapor pressure of the water. Let me share again the page of the experiment. Since the vapor pressure depends on the temperature, we will use this table, vapor pressure of water at various temperatures. So go to the write-up and look at that table. In our case, what is our pressure? We have to look at what is the temperature. In my case, the temperature is 21 Celsius. So I come to the table, you will see in your data, and you have to look at your temperature. In my case, because the temperature is 21 Celsius, the vapor pressure in the tube equals 18.7. So that data will be obtained from that table. So very good. So you know now where to obtain the vapor pressure of the water. In our case is 18.7. Both the same. We are going to do two trials. 18.7 torr. What else do we need to calculate? Volume of hydrogen gas in liters. The only thing that we need to do, the volume is given in the red data. So we just need to convert the milliliters to liters. So let's look back. Let's do the trial one. 31.5 volume of hydrogen, 31.2 milliliters. So all I have to do for trial one is 35.2 mLs. And then I know you probably do it directly, divided by 1,000. But another way is 1 liter equals 1,000 milliliters. So for trial one, I obtain 0.0352 liters. That is for trial one. Then it says temperature of hydrogen gas in Kelvin. What do we need to do? They give us the temperature in Celsius. So we know that the temperature in Kelvin equals the temperature in Celsius plus 273.15, and that's all we have to do to convert the temperature into kelvins. In my case, it will be 21.0 plus the number to convert is 273.15, and that equals, in my case, 294.2 Kelvin. Very good. Now they are asking for the moles of hydrogen gas. How do we calculate that? Let's look at the equation again. We know what is the chemical reaction. Magnesium plus hydrochloric acid 2 moles is going to give you magnesium chloride plus hydrogen gas. Very good. So let's look at the stoichiometry of the reaction. 1 mole of magnesium forms 1 mole of hydrogen gas. That means that the number of moles of hydrogen gas equals the number of moles of magnesium. Number of moles of hydrogen is going to be the same as the number of moles of hydrogen. And then how do I, as the number of moles of magnesium. And how do I calculate the number of moles of magnesium? What do you need to use? You need to use the mass. So when you go back here, you have the mass of magnesium. For the trial one is 0.035 grams. So then when I have to do the calculations, here is going to be 0.035 grams of magnesium divided by the molar mass. We know that 1 mole of magnesium, the atomic weight is 24.31 grams. When I do these calculations, I obtain what number did for my data. Let's see. For my data, I obtained 0.0014. Another 4. And that is the moles of hydrogen gas. Now comes the pressure. How do we calculate the pressure of the hydrogen? We talked a little bit, right? What did we say? We say that we assume that the atmospheric pressure equals the vapor pressure of the water plus the pressure of the hydrogen. But we are interested in the pressure of the hydrogen. So the pressure of the hydrogen equals the atmospheric pressure minus the vapor pressure of the water. For my data, the atmospheric pressure is given. In our case, for me, is 762 atm minus what? The vapor pressure of the water. And we already have that because we went to the table and we calculated that. So that will be, what was the vapor pressure? It was 18.7 atm. And that equals, but it was 18.7 torr. So I have to convert actually the torrs into the atm. So how do we convert that? Let me look at the data of the atmospheric pressure. The atmospheric pressure is 762 torr as well. So let me make sure the units are correct. So we said, let's review it. The pressure of the hydrogen equals the atmospheric pressure minus the vapor pressure of the water. And the units are in torr so far. So we complete this, we do 762 minus 18, and we obtain a value of 743.3 torr. Very good. But we know that 760, we know that 1 atm equals 760 torrs. So if we divide the torrs, the value in the units of torr by 760, we are going to obtain with my data 0.9780 atm, because they are asking for the hydrogen gas in atmosphere. So look again. First, what we did the atmospheric pressure, (762 torr) minus 18.7, the vapor pressure that we found in the table, the vapor pressure of the water. Once we obtain the value in torrs, we convert it into atm just by dividing by 760. So this is how we calculate the pressure. And then the last part, because we have the pressure, we have the volume, we have the number of moles, we have the temperature, we can calculate now the value of R. R equals what? With my data for trial 1, the pressure, we just calculated 0. Let me use 0.09780 atm. We multiply that by the volume, 0.0352. The volume has to be in liters. And then the number of moles that we calculated, in my case, is 1 1.44, and then multiply by the temperature in Kelvin. 294 times 15 Kelvin. When I do that, I obtain a value of R for trial 1 that is 0.08127, and the units are liters per ATM per Kelvin per mole. These are the units of R, of the constant of the gases. Very good. So why did we do that? Because we are using that equation. We know that pressure times volume equals the number of moles times the constant of the gases times the temperature. So if we are looking for the R, it's going to be pressure times volume divided by number of moles and temperature. Then you're going to do the same for trial 2. And then you are going to calculate the average. How do we calculate the average? The average is just, you have the value of the trial 1, you add the value of the trial 2 divided by 2. And that is going to give you the value of R, that is the average. Very good. And then they ask for the percent error between your value and the theoretical value of R. The theoretical value of R, they are saying use 0.0206 liters per ATM per mole and per Kelvin. So how do we calculate the percent error? You know the formula of the percent error. The percent error of the R is going to be what? The experimental value of R that you obtain minus the theoretical value that is given divided by the theoretical value multiplied by 100. This is the formula. So how are we going to do? What are our numbers? When we use the experimental value, we are going to use the average. So for me, it's going to be 0.08145. This is my experimental value minus the theoretical value, the one accepted. And then this is going to be multiplied by 100 and divided by the theoretical value. Again, 0.08206. When I do that, for me, equals 0.7434. liters per ATM. No, this is the percentage error. So this doesn't have units. It's just 0.7434. That is the percentage error. Very good. So this is basically a very short experiment. And let's look at two questions that are at the bottom. Let's erase here. One question. It says the hydrogen generated in this lab was a product of the reaction between magnesium and hydrochloric acid. Which of the reactants is the limiting reactant? How do we do that? You know the stoichiometry of the reaction, and you know when you look at the data how many moles you calculated the number of moles of magnesium, which is the same number of moles as hydrogen. You have the mass of the magnesium that reacted, and you convert it in a previous step to the number of moles. In my case, was 0.144 moles. So how do you know that if the magnesium is the limiting reagent or the hydrochloric acid? You know that you added 10 ml when you read the procedure, you added 10 ml of hydrochloric acid, 6 molars. So the number of moles of hydrochloric acid is going to be, we added 10 ml, but we have to write this volume times concentration. So if I want the volume in liters, I added 10 ml and I converted into liters. And I multiply that by the molarity, 6 moles per liter. My value is 0.06 moles. And you know that the reaction is 1 to 2. 1 mole of magnesium reacts to 2 moles of hydrochloric acid. But here we have much more than that this number 0.00144 times 2. So the limiting reagent is going to be magnesium. And we know that the reaction, when all the magnesium is gone and there is no more hydrogen gas, then we know the reaction is complete. And then there is another question. It says, suppose that when we inverted the eudometer, a bubble of air became trapped inside the tube. Would this make your experiment value of R larger, smaller, or have no effect? You know what formula we are using, right? R equals pressure times volume divided by number of moles and the temperature in Kelvin. So if we have an experimental value of the volume higher, than the true value, the R is going to be higher. If we have a bubble of air, our experimental volume is higher than the true volume. Part of that volume is occupied by the bubble. And because the volume is in the numerator, if the volume experimental value is higher, we will obtain a higher experimental value of the R. This is a short experiment, and this will conclude our workshop today, and I want to thank everybody for being here.